Okay, welcome back. This is a problem from the Regional Math Olympiad in 2017, Indian RMO. We must show that this inequality is true for real numbers x, y, z that is bigger than 1. So the inequality is x minus 1 over y minus 1 plus y minus 1 over z minus 1 plus z minus 1 over x minus 1 bigger than or equal to x plus 1 over y plus 1 plus y plus 1 over z plus 1 plus z plus 1 over x plus 1. So notice that on the left hand side we have the x, y, z has we subtract by 1 on each of the numerator and denominator, and on the right hand side we add plus 1. So the difference between each of the numerator in association and the denominator in association is 2. The difference is 2, right? Okay, so let us solve this problem. In this video, I will show 2 solutions for this problem. We have 2 solutions for this to show this inequality is true. So I will start with the first solution. We will rewrite the inequality. So I will move the right hand side to the left hand side. So I just subtract both sides by the right hand side, and I group the x over y terms and y over z terms and z over x terms. So we have this. So the original inequality is equivalent with this one, and they must be a non-negative. And then we just simplify each group here. We combine the denominator, so we have this one is y squared minus 1, the denominator, and the numerator is, well, it is easy to see here. This is just combining the 2 fractions for each group. And then if you simplify the numerator, each of the numerator, you can easily see there is a cancellation. For example, here x times y will be cancelled with minus x times y over here. Also for the others, yz will be cancelled with minus yz, and then zx cancelled with minus zx. And also minus 1 will be cancelled with plus 1 for each of the numerator, and you can check by yourself. The numerator will be just 2x minus y, and then 2y minus z, and 2z minus x. So this is the simplified version of the original inequality. As you can see, this inequality is symmetric. Okay, so this will be the inequality that we will prove. This inequality, and you can see here we can factor out by 2, so the 2 can be cancelled. 2 is cancelled, so we have this inequality. So this inequality is symmetric. So without loss of generality, we can just take x as the maximum among x, y, z. But we have 2 possibilities. Either y is bigger than or equal to z, or z is bigger than or equal to y. Now for the first case, where if y is bigger than or equal to z, we will rewrite this left hand side of the inequality that we will prove, right? And then notice this last term, we just add y minus y. Just add y minus y. And so we can get a z and y for this term, and x and y for the first term right here. So we have minus x minus y and minus y minus z. And we can combine this with the other 2 terms right here. Involves x, y, and y, z. So we will get here, it is easy to check, x minus y times 1 over y squared minus 1 minus 1 over x squared minus 1, and then plus y minus z times 1 over z squared minus 1 minus 1 over x squared minus 1. And I add inequality here because it is obviously non-negative, right? because x is bigger than or equal to y, and then notice here that y is less than or equal to x. So y over y squared minus 1 is bigger than 1 over y squared minus 1 is bigger than or equal to 1 over x squared minus 1. Because the denominator here is bigger. So this minus this is non-negative. Also, similar reasoning is since z is less than or equal to x, so 1 over z squared minus 1 is bigger than or equal to 1 over x squared minus 1. Because this denominator is bigger than the z squared minus 1. So this minus this will be non-negative. So all of this is non-negative. So we are done proving the inequality for the case x bigger than or equal to y, bigger than or equal to z. And now for the other case, this is the other case, x bigger than or equal to z and bigger than or equal to y. So y is the minimum here. And then we just rewrite the left-hand side of the inequality that we want to prove like this. So we use the first term now. We add z and then minus z. And then we write it as x minus z plus z minus y. Notice x minus z can be combined with this term, z minus x over x squared minus 1, and z minus y can be combined with y minus z over z squared minus 1 right here. So it is easy to check. This will be x minus z times 1 over y squared minus 1 minus 1 over x squared minus 1 plus z minus y times 1 over y squared minus 1 minus 1 over z squared minus 1. You can easily check that, and I add the inequality that is bigger than or equal to 0, because it is obvious that this is non-negative, because x is bigger than or equal to z, non-negative, and then z is bigger than or equal to y, and since y is less than or equal to x, so we have that this fraction 1 over y squared minus 1 is bigger than or equal to this fraction 1 over x squared minus 1. Also the same thing for here. The y is less than or equal to z, right? Y is less than or equal to z, so this fraction is bigger than or equal to this fraction 1 over z squared minus 1. So each term here, we have 4 terms here. Look at it as 4 terms, this, and this, and each is non-negative. So all of this is non-negative. Again, we are done for this case. We have proved the inequality. So we have proved this inequality. This is the first solution for this RMO problem. And now let us move on to the second solution. Now this solution is quite interesting and it is quite short. We use a substitution for this second solution. I rewrite the problem here. This is the inequality that we want to prove. Notice that this is the original problem. X, y, z is bigger than 1. We must prove this inequality. Now this is where the difference matters. You can see that each of the x minus 1, x plus 1, and then y minus 1 and y plus 1, each of them has difference of 2, right? The difference is 2. X minus 1 to x plus 1 has distance is 2. That matters here. And okay, so now let, again, without loss of generality, let z be the minimum. And we use substitution now. Let a be x minus 1, and x minus 1 will be positive, of course. And then b is y minus 1, and c is z minus 1. And since z is the minimum of x, y, z, so c is also the minimum of a, b, c. So the inequality using in terms of a, b, c is this. You can see here, it is quite clear now that the difference is 2, right? A and a plus 2, b and b plus 2, c and c plus 2. The difference is 2, and this will help us solve the problem. Okay, so now I will write the left hand side as this. I add a new terms here, b per a minus b per a and minus 2 and then plus 2. So we can do this, right? And then I group this, a over b plus b over a minus 2. So I will get here, this one right here is a minus b squared over ab. Okay, and then the b over c plus c over a minus b over a is ab plus c squared minus bc over ac. And then I just add the new term here, plus 3 and minus 3, because I want here to be minus 1 instead of plus 2. I want it to be minus 1. So we will get here, this is minus 1 and this is plus 3. And minus 1 can be changed by minus ac over ac. So we get here, the second term is a minus c times b minus c over ac plus 3. Now what's special about this simplified form is that the numerator is difference, that is a minus b and then a minus c and b minus c, and the denominator is multiplication. No difference at all. Now this really matters, as you will see later. So the left hand side that we want to prove become this one. For the right hand side, we can do exactly the same process that we get to the new left hand side, but for the variables a plus 2, b plus 2 and c plus 2. You can check using the same steps as before. We'll get this, right? You can see here, this is basically the same thing as the left hand side, but we just change the variables a, b and c with a plus 2, b plus 2 and c plus 2. Now this where the difference and the multiplication position matters, because in the difference, a plus 2 minus b plus 2, the 2 will be cancelled. You can see here a plus 2 minus b plus 2 and then a plus 2 minus c plus 2 and then b plus 2 minus c plus 2. The number 2 will be cancelled, so the difference will be cancelled, but in the denominator, there is no significant difference. And you can see now, the numerator here, after we eliminate the number 2 here, the numerator is exactly the same as the left hand side. So we can compare only the denominator, and this makes the proving easier, much more easier. Okay, so now this is the inequality that we want to prove, but this is clearly obvious because the numerator is the same. The difference is only in the denominator, and we can easily prove this. A minus c and b minus c is non-negative because c is the minimum, right? C is the smallest one. And then 1 over ab is clearly bigger than 1 over a plus 2 times b plus 2. And 1 over ac is bigger than 1 over a plus 2 times c plus 2. That is obvious. So a minus b squared over ab is bigger than or equal to a minus b squared over a2 times b plus 2. We just compare the denominator, and then a minus c times b minus c is non-negative, and ac is bigger than, 1 over ac is bigger than or equal to 1 over a plus 2 times c plus 2. Okay, and then 3, well, just leave it there. So it is obvious that this inequality is true. So this is the second solution of this inequality from the Indian Regional Math Olympiad 2017. Okay, that's it. Thanks for watching and see you on my next videos.